Hi there, my name is Sebastian and this is my submission for the 3 Blue 1 Brown math exposition that occurs this summer. So I'm really excited to show you this idea that I'm trying to explain because I was trying to understand the Jacobian matrix. I have to tell you that this idea is a little bit original to me at least, and I'm not really sure if it makes sense that much. So in the title that I've wrote here, The Bridge Between Linear Algebra and Calculus, I'm really hoping you can come up with me and construct this bridge so we can understand together. So of course, in order to understand everything, we need some concepts of linear algebra and calculus. And these concepts are, for linear algebra we need linear transformations, of course, and the geometric intuition behind them. And for calculus, well, not a lot about calculus, more like calculus 3. And this partial derivatives of transformation, we need to understand what they are. I've written the definition here, you probably don't really see much here. I'm going to restate everything, but first, linear transformations, yes? These are the two properties of linear transformations. You should know them, but I've taken the liberty to rewrite them here so I can remind you. And of course, because of these two properties, we introduce something called matrix. And with the help of the matrix, we can write any linear transformation, let's say, that I didn't mention, A times V, where A is a matrix and F is a transformation. We can write any transformation like this. And we call this matrix A, the matrix is associated with the transformation, of course. And you see here that we are going to work in the plane for a better intuition and hopefully generalize to n-dimensional space. And that's exciting, or it should be. So we don't need this anymore. And now on to partial derivatives, yes? So I've taken the liberty to work in the plane as well. And we have two partial derivatives, of course, of a transformation. And these are, in the point x0, y0, the limit as delta x a distance. This is a distance that I haven't defined anywhere else, but you hopefully can see it here, as delta x goes to 0, of the fraction, or how can I actually say that it's not actually a fraction, is a ratio, yes. The ratio between the difference here divided by this little distance delta x, and that is the partial derivative with respect to x here. And the same goes for y, and I hope you know these two. Something else that I wanted to say, that t here of x and y shall be u of x and y times the base vector I plus v of x and y times the little vector j. And of course, when you take the partial derivative here, this, let me delete a little bit of this, d at dx acts as a linear operator to u and v. And we get, we're going to delete that in a moment, acts as du dx I plus and as you might already guess, these two vectors are constant, and that's why I'm not taking the derivative of everything. So with that out of the way, we shall go and do some experimentations, right? So I've deleted everything that wasn't necessary to tell you that once you saw that the matrix associated with a linear transformation, my idea is how can we understand the Jacobian matrix that is often associated with a general transformation. So the point is that when I heard about the Jacobian, I thought that if you take a random transformation x and y here, you can write it exactly as a linear transformation, but with the Jacobian instead of the matrix associated with the linear transformation. So if this is a transformation that has the components u and v, I could write it like this. I don't really recall the order of everything, but that doesn't matter because we can interchange them later. Of course, this is the matrix form of a vector. You should be familiar with that. So I thought I could write it like this. But this is wrong. No, this is wrong. Because I verified using some examples. And if you're not convinced it is wrong, you can try it on your own. But I'm not going to try it here because I know it's wrong. So my question was, well, how can you say then that the Jacobian is the associated matrix of a general transformation if that doesn't apply? Well, we are going to see how it applies because it's something tricky. So most likely you have heard about the term local linearity. And once I heard about the Jacobian, everybody would say that it applies to a general transformation only locally. So my idea was, why not start from there? So I needed a notion to describe myself local linearity, all right? So let's take a point in the plane that I'm going to call P that has these coordinates. And let's say we have another point, N, farther away from P. So I'm going to call this N of these coordinates. But of course, N would have any coordinates, let's say X and Y, but I've defined X as this and Y as this. Why is that? Because I wanted a distance right here, delta X and delta Y. I hope you can see that. And then I got a rectangle. Of course, you should know where this is going actually, because it's quite simple. And I've denoted these 2 points as M and Q. And this would be the area of the rectangle, but that's not really important. And now that I've got this rectangle, I want to see what happens to it when I apply the transformation to the whole plane. And here is a tricky part because this plane needs to be filled some kind. I mean, what do I mean by filled? I mean that it doesn't have to, it shouldn't have holes in it. Because if it does, then I can't get N as close as I want to P. So my idea of local linearity was that if I can get an N anywhere in the plane close to P, I can get N as close as I want to P. But that would mean that the vector Pn here, this vector, would tend to be 0, right? So then I defined the vector Pn, and as you can see, it's just delta x I plus delta y j. Interesting, yes? If this vector tends to be 0, then these two tend to be 0. And you might recall that we have something called the differential in vector form here. So you might see where this is going. Then I defined Pn as being delta r, being this. If you don't see why Pn is what I wrote here, you can actually write r of p, which is x naught, y naught, etc. and r of n, and that is x naught plus delta x and y naught plus delta y. Once you take the difference, you get this. So if I can get n as close as I want to p, then this delta r becomes dr, right? Becomes the differential, which is this. Right, this is an ugly y. Okay, that out of the way. Now there's something interesting here, because I want you to see something else. The coordinates of m, which I'm going to write here, are x naught plus delta x and y naught. And the coordinates of q are x naught and y naught plus delta y. These 2 points shall help us. Why? Because once I take the transformation, I want to see what happens to them as well. These are not vectors, these are points. The vectors that we are going to use are PM and PQ. And you might see rather odd here that PM plus PQ is actually PN. And that is very important, because this here I don't want to change, even though it could change, you see, because we shall talk about it once we are done with this. So this is actually this is an important statement that we are going to use once we take the transformation. So what happens? What happens when we take the transformation of this? I'm going to draw another plane, but I want that to remain there. Okay, so I've drawn another plane there, and I've drawn the conclusions that we are going to use next. So now you might want to take this a little bit slowly. So once the transformation happens, and if the transformation doesn't get any gaps in the plane, we don't need gaps here, P goes to P prime, right? But I'm going to call the coordinates of P prime U0 and V0, right? Why? Because the U0 here shall be a function of x naught and y naught, and V0 shall be another function of x naught and y naught. So this is P prime. Okay, so far so good. What happens to n? Well, it becomes n prime. Of the coordinates, let's say u and v. The fact is here that most likely you should understand that this rectangle can become a surface. What do I mean by a surface? I mean something like this. Something curved. Something like that. You might recognize this from a course of Calculus 3. And that is interesting. I forgot the name that we actually give these kinds of shapes, although it has to do something with the pirates. But otherwise, if I can get n as close as I want to p, that's what I believe happens. I'm not really sure about this. That's why we construct this bridge together. We can exchange ideas. So this rectangle turns into this kind of weird parallelogram-like shape. And here, this vector PM, not PN, this vector PM kind of becomes a curve, right? And this too. But if I can get n as close as I want to p, then n prime shall be very close to p prime, such that these two curves will become lines. And thus, I get a parallelogram. And of course it is much easier to work with a parallelogram than with a rectangle. What's next then? Well, next I'm going to denote these as m prime and q prime. As you can see, by the rule of the parallelogram, p prime m prime plus m prime n prime shall give me p prime n prime. So the actual reason why I want p prime n prime is that p prime, or the coordinates u0, v0, can be written, r of p prime can be written as u0i plus v0j. But what is this? That is actually t of x0, y0, because I assume the transformation is called t. All right. And if we take r of n prime, I get ui plus vj. But this is the coordinates of the transformed version of n. And that is t of x naught plus delta x and y naught plus delta y. So by taking their difference, this minus this, I get p prime n prime, which is the kind of like a differential of the transformation if delta x and delta y tend to be 0, as we saw here. Okay, with that out of the way, so I want p prime n prime, but I don't want to take this difference because I don't know what this difference is. So I'm choosing the other way, which is this. We are going to use this. The same way delta r is pm plus pq, the same way p prime n prime, which I'm going to call from now on delta t, is p prime m prime plus m prime n prime, as we saw before. But as a reminder to you. So what is delta t then? Is the sum, of course, but what is p prime m prime then? P prime m prime, well, it's most likely t of x naught plus delta x, y naught. I was thinking if I already said the coordinates of m and q. I hope you remember them, even though I didn't put them here. Minus this. And this difference is very important, as you saw at the beginning of the video. Plus t, the coordinates of n prime, of q prime, x naught y0 plus delta y, minus t of x naught y naught. And that is interesting. We get two differences that we can write as this. And here's the interesting part. We shall divide this by delta x and this by delta y, so we can get the ratio of the derivative. Yes, you have guessed it. I hope you did. Okay, so we're back, and I've written what I wanted to write, and of course we can simplify this anytime. But I want you to really now see that we can take the limit as delta x and delta y goes to 0, exactly as we did here. And of course, this shall become dt, and these dy and dx. And you already know what these two become. So I really need a space, so I'll be back. Okay, so we're back. I might have teleported from there to here. And we see now that this forms the differential of the transformation. And that is interesting because the resemblance is very interesting with if t wasn't a vector, if it was a value. So you might see here that this is a vector, and this is kind of a scalar because I already can write this in this too. So what is this truly? Well, it's a linear combination, of course. That is interesting because we know from linear algebra that any linear combination can be written in a matrix form. So the only remaining thing to do is to write these two in vector form or matrix form. And we shall do this in a bit, deleting everything because we don't need it anymore. So of course you remember that this has the operator in front of it, so its coordinates shall be, let's write it in the matrix form, du dx and in this point, and dv dx also in this point, times the differential dx, plus the same goes for this. So we get this result, right? Very interesting. So now we can unite it in the matrix form. And you shall see how this actually resembles the derivative as you were told it does. You see now that I think I've misplaced the variables here once I wrote the Jacobian for the first time in the video. It's a tricky resemblance that shall help you even in complex analysis. Interesting, right? So you get dx dy here, and that is the differential dr. And this is the Jacobian matrix exactly in the point I wrote, exactly in the point P of x naught y naught. And this is interesting, this is dt here. It's kind of a long road, but this applies with the d in front of. So the only thing that we could have added at the beginning of the video was a little d here in front of everything. We know that this does not apply, but if we add d's everywhere, it does. Interesting, right? So the remaining factor to do, the only thing left to do is, of course, this was the conclusion. This was what I wanted to show you. But if you remember, if you have a one value function, f of x, you can approximate f of x as df dx in x0, for example, times x minus x0 plus f of x0. Do you remember this? This is the linear approximation. And the thing is, the same way goes for this, for the transformation, for something so general that you might have not intuitively said it would apply. And we get to this. The resemblance is very interesting here because I've replaced the differential with an actual difference, and I've added here as if t of x and y minus t of x naught y naught was not a differential but an actual difference. And this approximation works. It works for any transformation, even if t is linear. And this is the linear approximation for any transformation, such that it generalizes everything. This works in the plane, and I told you at the beginning of the video that it works in an n-dimensional space. So, if this matrix is actually an n by n matrix, and this is n coordinate vector, it works the same way it works, but it would require me the whole board to write it. So that's it, and if you didn't really comprehend everything, or you want to try some exercises, I've left some in the description of the video so you can try it by yourself. Very interesting, right? So that's it, and thank you for your attention, and see you.